So by now, you're basically feeding half the planet with the ammonia we produce. Problem is that this is a high temperature, high pressure process, and it's responsible for more than 2% of global CO2 emissions. So, and we produce like quite a lot of ammonia. So the goal was to try to see if we can have an electrochemical way of producing ammonia. So the system we're looking at is rather complex, like multi-step process. Do you see my pointer? Maybe. Okay.
Yes. Yeah.
Okay, cool. So it starts with plating lithium. Then you will use that lithium with nitrogen in the system to produce lithium nitride. Then you'll use a proton donor in the system to swap that lithium with a hydrogen, and then you get ammonia. So it's a rather complex system. So there you go. So the data I'm showing we're taking that SNS of the liquids reflectometer. It doesn't quite look like this anymore. We've just rebuilt a bunch of it this year. It's a time-of-flight instrument. So let me just explain a few things that will explain the type of data that you're going to see in a minute. So our repetition rate is 60 hertz. Our detector is about 16 meters away from our moderator, which means that we have a very narrow wavelength band, unfortunately. Which means that if you measure a full measurement, it'll be made of several, usually 7 or 8 smaller runs. So each color here is a different run, which means that if you want to do time resolve, then what you'll do is that you'll pick your favorite one here, and then you'll just sit there, count, and then since we capture every neutron individually, then we'll just slice the data after the fact as we wish. So it kind of looks like this. You notice that this is a little bit wider than those here, so we can play this trick of basically blocking every second pulse and operating at 30 hertz, which gives us a 7 angstrom band, which is a little bit better. So it's not that great. Other instruments do this better than us, but this is what we have. So what you'll do is that you'll just measure your steady state, measure it to death, then fit it so that you understand what you're starting with, and then use that information to process the data that you'll acquire on that narrower Q range. So coming back to ammonia, so our first study was use the Moly electrode. Our electrolyte was THF, saturated with nitrogen. Our source of lithium was lithium perchlorate, and we had 1% volume fraction of ethanol as our proton donor. So you put this in this little cell here, apply constant current. This is very low current as these things are. We'll see later what the types of current that people are using. But basically, the point is to try to understand what happens at the surface at currents that allow us to basically have something that's still smooth and that we can understand. And the reason we use THF is that if you use an aqueous solution, then you would be fighting against hydrogen evolution reaction and basically produce hydrogen. So the results we got for this first study were kind of nice, where we could see the plated layer, the lithium rich layer being plated as the first step of this 3-step process. Growing here, SLD goes down. This is my SLD profile. So as we uptake lithium, then SLD of that plated layer will go down. We can compare with and without ethanol, and then you see that if you don't have ethanol, so you don't have the proton donor for the very last step, then you're not really using the layer that you plated, and then it remains a little bit thicker. One thing that was interesting is that although those were measurements, so every point here is a minute, and we measured many minutes, but we were not necessarily able to fit that data or understand that data. It gets a little bit wild after a little bit. But the first few minutes, you could see it was consistent with one layer. So no clear evidence of any SEI type layer that you would have like in a battery system, for instance, at this point. And this is interesting because there was a study that proposed or that showed that if you use that same system with short cycles, so instead of just applying constant current for, as long as you want to produce ammonia, then you would do it for a minute, then go back to open circuit and let things relax for 3 to 8 minutes, and then do it again. And here they were using 2 milliamp per centimeter squared, which with this system we were not able to achieve. But we did that at a lower current. So you see here the potential drops as you apply your current. And then we were able, in this case, to measure little reflectivity curves every 15 seconds. So you start by measuring your steady state at open circuit, you apply constant current, and then we basically measured time resolve for a couple of minutes. And then you get something like this. So we're not able to process the full 2 minutes, mainly because it looks kind of like this. So you kind of start seeing the plated layer form. After a while, you may start seeing evidence of something else happening on the surface, but you reach a point where your error bars on that SLD profile, so this is a 90% confidence level interval, gets big enough that you kind of don't know what's going on at this point, so we stopped. The thing that's interesting is that, a little bit like they were saying with the short cycles, you start seeing the plated layer form, and then a little bit of SEI perhaps, and then as you go back to open circuit, you see all these things shrink back down. So we measured time resolve like for the whole period of time that we were applying constant current, and there's a period in the middle where we're unable to process that data. But you can see that the plate layer shrinks as well. So you're still, as you're going back to open circuit and letting things relax, then you're still using that plate layer, presumably to produce ammonia. Then you apply a constant current again, and then you see things grow back. So kind of devise this picture here where you start with your as prepared film at open circuit, you apply constant current, and then you let it relax. And then if you just had steady state measurements, you would measure here at your initial CV, then you would measure in that dip here, and then you might be tempted to think that not much is happening, but there's other stuff happening in between, and you wouldn't be able to see that if you didn't do time resolve. So that was not the greatest system necessarily to do this type of study. I mean, it was pretty hard. So we changed things around recently in the last couple of years, where instead of moly, we're using copper, which gives us better contrast. Changed our lithium source to LiBF4, and now we get better quality data for sure. So this is just an example of one measurement where I can actually slice my data to 5-second intervals if I want to. So, and then the question is, you have all this data, how do you fit it? The naive approach, or the easiest approach, would be more of a recursive Bayesian approach, where I fit my initial data, I do full error analysis, I have a probability distribution for my parameters, and then I pick those that are likely to change. And then I can add a prior to my cost function, where I'm also adding a little knob here to see how to dial in how harsh I want to be with that constraint, namely because you know your system will change, so you want to be able to give it a little constraint in the right direction, but not too much, because you still want it to change. And for data that's pretty like this, it works fairly well. So here I show like the initial state, the final state, and then you see in between the layer grow, SEI formation, and then you can plot this as a function of time, and then basically access those timescales, which is kind of nice. But the The problem, though, is that with as narrow a Q range, and of course, like you have other problems, like what if you don't know your final state or your initial state very well? What if there's multiple timescales? And in the end, I found that, if your sampling rate sort of, if you want to use that approach, has to be matched to your rate of change. So if you sample too fast, for instance, then you can have a lot of little incremental changes that will kind of wash out your prior. Conversely, if your sampling rate is too slow, then you need those big changes, and then your prior is preventing you. So fitting this kind of looks like this, where you kind of choose how harsh you want to be with your prior information. You select your delta t for how you're going to slice the data. You may decide on a time direction. If you have both final and initial state, it doesn't really matter. Pick your fit parameters and adjust fit ranges, just like you would normally do. Run the fits, so go for coffee and then come back an hour later. Then assess your results and do the same again until you get them all that makes sense. So one thing I tried to look at is, can I use another technique to fit that data? So I started looking at reinforcement learning to fit time resolved data. And so just as a very quick intro, so with reinforcement learning, you basically try to optimize an action as a given a state within an environment following a trajectories or timeline of actions. And with each action, you get a reward, basically. So that tells you how good you're doing. And the process, the algorithm, will optimize, basically try to define the best action for a state that will likely lead to the best overall reward, so the sum of all rewards. So basically, I like to use this little dog here, where given the dog being on a post, then he gets to pick, like, the parameters of his jump, how much energy he's gonna use for a jump, and then so that's the action. And then the state that you land with is that, well, are you in on the next post, or are you fallen? And reinforcement learning would be, if you define what an action is, what the states are, then we'll be very good at solving that problem of the dog getting to the bone. So what we did here is map this to this here, where a state is a structure state. So it's my reflectivity curve at each time t. My action, so given that state, will be the fit parameters for that particular state. And my reward will be minus chi-squared, so it's maximizing the reward. And you can add any constraint that you want. So the thing that's different from traditional reinforcement learning is that here, the time series of states is predetermined. So I'm basically just using their fitter to try to solve the best sequence of actions, so of structure parameters, for this one known trajectory. So basically what I'm doing is fitting not one curve at a time recursively, but I'm fitting the whole data set at one time. And works fairly well. If you don't have a ton of data, it's actually quicker than doing the recursive thing. And here I'm comparing, for instance, for that same system, in green is the reinforcement learning, and in red is the recursive fit. So this is the SLD of my SCI layer. This is its thickness. There's an interesting little gap here, mostly because I didn't work very hard in fitting it with the Bayesian approach. But one thing that's interesting is that the reinforcement learning, if it's preferable to have a big jump, it will do that, whereas the Bayesian approach tends not to do that. Yeah, a couple details about like how it works or why it's interesting. I find it interesting. There's multiple engines that you could use for reinforcement learning. I use the soft actor critic, which is kind of neat because it adds a entropy term. to its cost function. So it's good at sort of exploring around your solution. It's also stochastic, so you get a probability distribution at the end. And I like this quote here from the original paper for that engine that says that in problem settings where multiple actions seem equally attractive, the policy will commit equal probability mass to those actions, which if you're fitting reflectometry and you always have multiple solutions, it's kind of an interesting, it sounds good. So last slide, just giving a little bit of a better example of how the reinforcement learning actually works. This is a system I'm less familiar with. It's from this paper where they measure the initial final state and you get the time resolved data in between. And towards the end, it looks good. At the beginning, it looks good. And in the middle, there's kind of this weird data here. And one hypothesis we had was that because if you were to fit this with like just one model, it wouldn't work. It would fail in the middle. So what we came up with is a hypothesis where you have sort of a patchy system where, I guess I didn't explain this, but this is a polymer that you apply a potential to, and it basically grabs ions in electrolyte. And so we model that as a patchy system where parts of this, you start with the initial layer surface, and then in patches, it will start to uptake those ions. And so you have parts of the system that is not changing and part of the system that is changing. So you have a kind of sum of two different types of samples. So model that with the layer parameters for that swelling layer, and then a mixing parameters that says how much of my initial state is still left in my overall system. And here I compare the reinforcement learning in blue and the recursive fit in orange here. And surprisingly, for a complex system like this, they agree fairly well. So it's quite happy that reinforcement learning in the end is a method that I'm not 100% sold on to use, but it's kind of interesting that you can use tools that are not necessarily meant as a traditional fitter for what we do, but can be used and are pretty efficient. Anyway, so that's my story. And I should probably thank all these people who contributed to all this work. Thank you.